Hello, I'm Yipai Du from Hong Kong University of Science and Technology Robotics Institute. I'm going to introduce our recent work on ICRA2021, high-resolution three-dimensional contact deformation tracking for FingerVision for sensor with dense random color pattern. This is the outline. Our approach mainly consists of four parts: dense random color sensor design, optical flow with adaptive referencing, Gaussian density for depth inferencing, and a guided filter for post-processing. As we are moving from industrial-level robot to domestic-level robots, the environment is becoming more and more unstructured. Therefore, it poses difficulty for the robot to behave more adaptively. On the perception side, tactile sensing, as a very important sensing modality, is becoming important. Traditionally, there are piezoresistive, capacitive, piezoelectric, and optical tactile sensors. However, the sensing resolution is not very high. A recent trend is to use a camera to capture the deformation on a gel, and using computer vision and deep learning techniques, we can recover the contact information. Here are some typical examples for vision-based tactile sensors. GelSet and GelSlim are from MIT, and Digit is from Facebook. They all used photometric stereos for the contact deformation estimation. They are also equipped with the tracking dots, so the shear information can also be captured. Carmelo Sfraza and Raffaello Dandella from ETH Zurich proposed to use fluorescent particles that are randomly distributed within the gel. They used dense optical flow to track the 2D information and then use a neural network to accurately estimate the force. Tactile family from Bristol University used trackable dots and Voronoi area to approximate the surface deformation. A research gap here is we want a vision-based tactile sensor that is simple to fabricate and calibrate, and we want the computation to be light-weighted. Also, the resolution should be high for contact modeling. Our sensor design uses the Raspberry Pi camera, which is very cheap and widely available. There is LED light to provide constant illumination. Random color pattern is used to track the high-resolution deformation information. We also use dense optical flow for tracking. It essentially calculates a translation vector UV for the template image to translate into the target image. However, when the sensor gel deforms, it undergoes a nonlinear transformation. For example, we can see when the contact is made using this cross, the peripheral regions, which is enclosed by the red curve, it undergoes the illumination changes, and also the patches are different. This nonlinear deformation cannot be easily tracked by single UV vector. We may want to calculate the frame-to-frame optical flow and then add them up for a more accurate estimate. However, in the long run, this will cause the error to accumulate. Therefore, we propose to use the adaptive referencing optical flow for the contact tracking. Essentially, we are running two optical flows in parallel. One is of high resolution, the other is of low resolution. We use a low resolution one to inverse warp the current image and compare it with the reference image. If we find the error is very large, this means we need to add the current image into the reference image stack, and later on it will be used as the reference image. We are also constantly checking if we can reduce the size of the reference image stack to make it more memory efficient. Then we use Gaussian density for depth inference. It is a density measure for particle distributions. The advantage is that it is translation equivariant, meaning for the same particles when they are shifted, the corresponding density is also shifted. So the density drop means there is a particle expansion, and this is correlated with contact depth. Because we want a positive correlation, we take the negative of this density, so it is proportional to the contact depth. To sum up, our pipeline consists of these 4 parts: random color tracking pattern, adaptive optical flow, Gaussian density, and finally a guided filter for post-processing. We show the optical flow tracking performance here. On the left-hand side, this is the optical flow magnitude without the adaptive strategy. The middle ones are the raw images. On the right-hand side, they are the magnitude with the adaptive strategy. We can see with the adaptive referencing, the optical flow tends to be smoother, and also at the contact boundaries, the boundaries are sharper and more straight. We also did an experiment for the linearity of the Gaussian density with respect to the contact depth. Here are 3 figures corresponding to 3 different indenters of different size. On each figure, there are 3 curves. Each of them corresponds to a contact made at the center of the sensor, the corner of the sensor, and the midpoint of the center and corner. As we can see, all these 9 curves shows a strong linearity. The correlation coefficient is over 0.98. We combine all these 9 curves and fit a single straight line as a depth predictor. The 9 curves combined, the data shows a correlation coefficient over 0.95. Here is a quantitative result. As we can see, the overall contact shape is successfully recovered. Also, because our indenter is mounted on a square platform, the multi-level indentation structure can also be captured. For example, in pair 8 and pair 11. We also have the quantitative results with the help of finite element method. We do an FEM simulation in Abacus, and the 3D deformation from Abacus is projected into the image plane using the calibrated camera model. The tracking pattern is then warped using this 2D optical flow field, and then we pass these synthesized images to our proposed pipeline to obtain an estimate of the contact depth. As we can see, the overall contact shape is recovered very well compared to the ground truth. The errors mainly occurred at the contact boundaries, so when the contact is larger, the total error increases. We also synthesized using the dotted marker instead of the dense random color pattern to show the effectiveness of our method. We can see the predicted contact depth is much worse compared to the dense one. In this paper, we presented a software-hardware co-design of an improved vision-based tactile sensor. It is easy to fabricate, simple to calibrate, with very fast process time, over 40 frames per second. It achieves satisfactory deformation tracking performance and contact depth estimation. In the future, we hope to verify the versatility of the framework with more variants of vision-based tactile sensors. We hope to improve the accuracy of estimation, especially at the contact boundaries. Finally, we hope to utilize the extracted deformation in dynamic manipulation tasks. Thank you.